Hello and welcome to the webinar, A Chlorine Pyramid, a new way to look at water balance. I'm Scott Webb, editor of Aqua Magazine, and today we have with us John Bereza, who really needs no introduction. Either you've had the John Bereza experience or you haven't, and in that case, nothing I can say will explain it. But I'm going to give you a few facts anyway. John is the Great Lakes Regional Sales Manager for Haviland Pool and Spa, a 21-year veteran of the Grand Rapids-based company. John specializes in employee training and consumer education. John and his wife live near Grand Rapids, Michigan, with their three boys. John is a board member of his local Little League, which is a fact that I didn't know as long as I've known him, and is an avid golfer, tennis player, and pickleballer, and a diehard fan of Detroit sports. And we won't get into that. I did want to mention a few things before we get going. If you have a question about something John is presenting, there's a button on the bottom of your screen. Send it our way. And secondly, I want to note that this is the first of a series on this topic. And so like any blockbuster, The Terminator, Friday the 13th, or what have you, there will be sequels. So look for those in the coming months. We've got a lot to cover today. A different take on pool chemistry. I think a very creative and helpful take, which I think you are all going to enjoy. I thought it was really refreshing. So without further ado, John, take it away.
All right. Thank you so much, Scott. Always a pleasure to spend any time with you. And thank you for this platform. And we do need to update the bio. I'm at 23 years now at Haviland, one step closer to
Oh,
death. So everything else is 100% correct. But thank you guys and welcome. We're going to cover about 40 slides today. And our program today is called the Chlorine Pyramid. As always, yes, what Scott said, jump in, ask questions. We'll try to get some of those answered during the live presentation. And then we'll have a chance to review this later on. The video link will be shared with all of you folks subscribing, watching today. It'll be posted tomorrow afternoon. I know that's a big one. And feel free to share that with any folks if you like it. So let's jump in. The pyramid really talks about the idea of chlorine being the key to maintaining your pool. For a long time, I've taught this program as pH being the key. Maintaining your pH helps maintain your chlorine, and then your alkalinity is your base. And we're just taking another take on it to give you a better idea or a different way to understand it. And we're also explaining this in a different way that I'll show you here in a second. So chlorine is the tip of the pyramid. This is what does the sanitizing. This is what does the killing of the bad things in your water. So we need that chlorine to be working at its best. And how do we do that? We maintain it through our level 2, our pH. Our pH needs to be spot on so that our chlorine can do the job we want it to do, and then it can work the most efficiently as possible. And how do we maintain our pH? We maintain our pH through alkalinity. It adds a base to support our pH. So we need our pH to be working. We need our alkalinity to support that. If you want to add one more step, and for me, this is more of a must than an additional add-on, add an additional base of borates. That additional buffering, larger base to help your pH is critical. That keeps everything in line and everything stable. And that's your chlorine pyramid. Now, when you look at a pyramid, it's not one face, it's not a triangle, it's multi-sided. So the same elements that we're going to talk about today in terms of keeping water clean, those same elements also have an impact on other things in your pool, like corrosion, LSI, for example. So the same elements we talk about here, we'll be talking about in later presentations, and why maintaining the water quality at the sacrifice of LSI and vice versa is critical. So if you change these components, you're affecting the other components. So it all comes together, and that's why we talk about this as a multi-sided pyramid instead of a triangle. So we'll talk about that at a later presentation. I also want to describe chlorine as a killer, and it is. It is an EPA registered pesticide. It is designed to kill things in your water, and that's what we want it to do. We want it to destroy pathogens, specifically the ones that make you sick. We also want to kill algae, things that grow in your water that are a nuisance. So we want that killing element to be at its peak. We want it at its best. So I want you to think of chlorine as a knife, and it gets dull and it gets sharp and it gets used in incorrect ways. This was almost called the chlorine killer, but I think we were getting maybe a little bit of a true crime audience that we didn't want. So we changed it. We didn't want these to be too popular, Scott. So we switching it specifically. We didn't want the YouTube algorithm to bring in an audience that didn't make sense. So let's talk about chlorine and pH. So your pH, we want at a 7.2 to 7.6 range. I promised when I sent out my LinkedIn there would be no math. This is not math, but this number, the 7.2 to 7.6, is kind of the pH-TA range where we would like it. Within different applications, this range might differ slightly depending on the pool surface, depending on the type of chemistry that you're using, depending on your environment. This might be tweaked a little bit, but that 7.2 to 7.6 range is ideal, with 7.4 being the key. But here's the issue. So if you get to the left, if your pH gets more acidic, and this pH scale goes from 0 to 14, 0 being very acidic, 14 being very alkaline. So the 0 is a much more aggressive number than the 14. That 0, as we move closer to that, that chlorine gets sharper and sharper. And in reality, as the pH reduces below 7, it gets sharper all the way to a 6 and maintains that to a pH of about 3. That is as sharp as chlorine gets. I want you to think about that, that a pH neutral and lower sharpens chlorine, makes it a more effective killer. If we go above a pH of neutral, above 7.6, the blade edge dulls. It slows down. It becomes an ineffective killer the higher we get pH. It dulls that blade and makes it worse. Let me show you a true life example of this in terms of chlorine in your water. That blue bar right down the middle is the 7.2 to 7.6 range. So you see a pH along the bottom left that goes on a scale from 6 to 10. And that red dashed line is chlorine's effectiveness in the water. That's the way I want you to think about it. It's actually hypochlorous acid, the percentage of chlorine that is hypochlorous acid, which is the killer in the water. So when you add chlorine to water, it converts to hypochlorous acid. But as the pH goes up, it converts over to another less effective form. So as we get to a pH of 7.2, you have 68% of your chlorine is hypochlorous acid, which is a killer. We want that number as high as possible. As the pH goes even higher, we're only at 45% effectiveness. Only 45% of that chlorine is hypochlorous acid. We've dropped significantly. We've lost a third of our potency, even within the proper range. Now imagine we get too high in that range. You've got a pH of 8, for example. Your chlorine is only 23% effective. You're talking about a third the potency at a pH of 8 versus a pH of 7. That's why chlorine and pH are critical. They are tied together. We do not want to be at that higher range of pH for that very reason. Again, the lower we are on that pH scale, the sharper the blade, and the higher we are, the duller the blade. Think about chlorine as killing the green stuff in your pool, chopping your algae, killing all of the bad bacteria in your water. We want that blade as sharp and effective as possible. This is within an ideal pH range. Now we get into an incorrect pH range. We're too high. Now we have a dull blade. And what do we have to do to compensate for that? we have to add more and more of this chlorine to be effective. A lot of times folks will say, hey, I keep adding chlorine to the water. I'm not getting a chlorine result, and I'm not getting my pool clear, but I've added so much chlorine. Well, you're adding this ineffective form of chlorine. This chlorine at a high pH, for example, one of the many reasons, and typically the major reason you're not getting a chlorine reading, is that the pH is incorrect. Even though you've added all of this high amount of chlorine, it's just not a good form of it. So here's your chlorine residual that we want in the water. We want 1 to 3 parts per million of chlorine in your water to make sure if things enter the water, there's something already existing, a residual of chlorine there to kill it. We need to have that in the water. And an ideal 1 to 3, 2 is a great spot to be. But I'll show you where really you can run at about a 1 part per million in a household pool very, very easily and have great looking water. Here's that same chart that I showed you earlier. This green bar is that hypochlorous acid. So that chart I showed you a second ago, this is the bar dropping from upper left to lower right as the pH climbs. It starts to lose its potency. It starts converting over to this thing called hypochlorite ions. Hypochlorite ions are a very, very ineffective killer of pathogens. So as the form of chlorine converts over, the hypochlorous acid drops off, so your chlorine isn't working effectively. And then you're creating this buildup of hypochlorite ions, which really aren't effective at all. That chart on the right is just a little bar graph that kind of shows, or a little chart that shows you where the pH ranges are and those percentages. Let me show you a little close up of that. Let's go back to that pH of 7 there. So at a pH of 7, you've got over 77% hypochlorite or hypochlorous acid. So you're about 3/4 potency. At a pH of 8, so you've gone up one increment in pH, you're only about 25%. So you're only about 25% of the good form of chlorine. So a 1 ppm chlorine level at a pH of 7 is the equivalent, essentially, of a 3 ppm chlorine level at a pH of 8. So you're talking about you would need to add 3 times more chlorine to your water to have the same amount of killing power solely based on pH. Has nothing to do with the contaminant level. So if I'm adding 1 part per million chlorine in my pool at a pH of 7, and my neighbor is at a pH of 8, he would need to add 3 times as much. As we add that up over the course of the season, that is both expensive and can have other harmful implications. And we'll show you that here in a second. So you got your chlorine, you got your pH. Now we're going to talk about alkalinity and borate. Those things are called buffers. Those are things that stop pH from moving in either direction. They buffer the water from the pH increasing or decreasing from things that enter your water, rain, swimmers, other waste materials. And we need those buffers to be as solid of a base as possible. If we have a small amount of buffering, if our alkalinity level is very low, if we don't have borates in the pool, this pH chlorine killing power is starting to tip. It's starting to waver. It's starting to bobble back and forth between very good killing and very poor killing ability because the pH is constantly swinging. It's both harmful to constantly being adjusting your pool, adding acids and bases to adjust your pool water. It's also costly to do this. So these buffers we want to be in line to help your pH. Here's one of the main reasons that we talk about pH. So every chemical field has its guy. And our guy is this guy, William Henry. And he lived a few years ago. And he developed this principle called Henry's law of solubility. And all you really need to know is this, is that water wants to be at equilibrium. It wants to be equal. So it wants the amount of dissolved gas that it's contained within itself to be the same as the dissolved gas in the atmosphere. And specifically, we worry about this with this thing, which is CO2, carbon dioxide. So water has carbon dioxide dissolved into it. You don't see it, you don't feel it, you don't realize it, but what it does is Carbon dioxide lowers the pH of water. You'll see some municipal systems that use carbon dioxide instead of acid to lower their pH. Carbon dioxide lowers the pH of water. Well, what happens is the carbon dioxide in your water is at a higher concentration than the carbon dioxide in the environment, in the air. So this Henry's law of solubility says, well, to be at equilibrium, water essentially spits out this carbon dioxide. So if you remove something that lowers the pH, you essentially are always increasing the pH. So Henry's law of solubility means simply this: water will always raise pH. It'll always increase in pH over time. It's slow and it's subtle, but it will always raise it. A little side effect of this, if you see that container on the right, if you're in a closed environment, say you're in a building that has very little airflow, the CO2 level may build up within that building, and now CO2 gets trapped in your water, and you might actually have the opposite effect where your pH is always reduced. We're not going to talk a lot about it here, but it's an interesting side effect of that. Let's talk about total alkalinity and pH. And you can't talk about that without talking about feet. pH and alkalinity are almost identical. They are so tied together. They are like your pointer toe and your big toe. If you're out there watching right now, I want you to just wiggle your pointer toe and then just wiggle your middle toe. And it's almost impossible, if not impossible, to move those. I'm going to get this foot off the screen
I
for you.
can't. I can't do it.
So the pH and alkalinity are so tied together. Moving one moves the other one. Folks that have been in the industry even a short period of time have that understanding that, oh, we're constantly trying to move alkalinity, but our pH moves, and we're trying to move pH, but our alkalinity moves. And it's tricky, and it absolutely is, because they are almost essentially tied together. So we talk about pH and alkalinity. We want them in these two ranges. We want our pH at that 7.2 range. We want our alkalinity to be at that 100 range because of this. Well, let me show you this. I forgot, I slid this graphic in at the last minute. I want you to think of pH as the hammer on the job site. It moves everything. You can use this tool to turn a nut, move a foundation. It does everything. It is the big weapon. It moves pH. It moves alkalinity. It does everything. So it's hard to adjust pH without affecting everything. But I want you to think of alkalinity as making those small adjustments to your alkalinity without really affecting your pH. Let me show you this graphic here about why this is important. So if we get a weather event, what happens to pH? You guys know this. When we get a rain, that pH can drift one way or the other. And without total alkalinity being locked in, that pH adjustment can be very, very dramatic. So that change, it's going to move a little bit, but the total alkalinity being in place is what's holding it from moving really, really fast. So if our total alkalinity drops down, for this example, like 60, we might see a very dramatic pH change, which we don't obviously want. We need to keep our pH in line. Let's talk about what total alkalinity and pH look like on the acid and alkaline scale, on the pH scale. You got 7 as your neutral. Your pH, your commercial residential pH increaser is about a 10.5. It's a chemistry that is relatively safe. That's why we give it to consumers. We don't give them sodium hydroxide or lye or things like that to increase their pH, because they can be dangerous. So we give them a fairly neutral. It's still at a 10.5. It increases your pH. But look where alkalinity lies. If you had an alkalinity increaser, we're only at about a pH of 8.5. We're not that far from neutral. We're not that far from where your pool water needs to be. So what it does is it adds alkalinity to the water. It increases your alkalinity through adding material things, carbonates typically, to your water without greatly affecting your pH. So if we want to raise the pH and alkalinity at the same time, we'll simply add pH increaser. But if you only want to raise alkalinity without affecting the pH too much, we'll add alkalinity increaser. It does have some effect on pH, but not nearly the effect that pH increaser and decreaser have on alkalinity. So you have your pH at 7, you have your, or 7.2, you have your total alkalinity at 100. What I want you to do next is you throw a borate in there at 50, right? And now we add this rainstorm again. And remember what happened during our last rainstorm? Our pH is shifting over and over again. Well, if you add this second level of buffering, then now that pH, your pH, which during regular rainstorm might increase by zero point 0.2, zero point 0.4, zero point 0.6, or move in the other direction by the same amount. If you add borates, you might not see any change in that pH. You might see a 50% decrease in that change. The borates add a second level of buffering that simply stop pH from moving to a pretty dramatic effect. So that's why we added it. If the key to maintaining chlorine is through pH, then adding a second buffer to that is key and critical. And that's why we like borates so much, amongst other things.
Hey, John, let me just break in here for just a second with our bonus round poll question for everyone watching at home. Please enter one of the responses you see on your screen. I'll read the question. What is the ideal length for a training video? Is it 2 minutes? Is it 5 minutes? Is it 15 minutes? Or longer? You don't have my favorite response, which is at least 6 hours. But if you would please take a moment and enter one of those responses, we'll get the results live here on the show. And we will then get a quick response from John.
So,
Oh, here we go.
oh, look at that. Well,
Look
I
at that.
love the longer thing. I don't know what my audience demographic is, but I know my teenagers, I didn't put 15 seconds on there as an option, but I think that's the length they would want. But I got to tell you, I'm a big audiobook fan. And Scott, I'm a quarter of the way through War and Peace. And that is not a quick read or a quick
No.
listen. So longer is what I typically like, so I get the full breadth of the story. But I appreciate the information, folks, and we are working on some new content, and that information always helps us to give you kind of a better, more refined way of doing this without all my pauses and coughs. So
Thank you.
here we go, guys. We just talked about chlorine and pH. We talked about alkalinity and borates adding that buffer. And then we talk about the remote dying. I think that, give me 1 second, Scott, because I think I might need to start this presentation because that, give me 1 second. I'm going to stop sharing for a moment and start the presentation back up. And hopefully we can get this quickly. And share. Almost technical difficulty. You can see where the video would come in handy here, guys.
We'll get it.
And let me
Okay.
get to the slide we're on. And hopefully. All right. So we have our chlorine, we have our pH, we have our alkalinity, we have our borates, we have our buffering system in place, but there are other problems. Problems bigger than slideshows collapsing. And here are some of those other problems. Is that chlorine, again, is a killer. It's a cold-blooded killer, but only in a perfect environment because it is also a very distracted killer. It does not always go after the things we want to. We want it to go after things like algae or things like bacteria, things that make you sick. But unfortunately, it goes after things like this: grease, urine. It goes after things that enter your water and it becomes combined with those things. It gets muddled down and it's no longer going after the bad things in your water. It's going after nuisances in your water. And that's really the problem with chlorine, is that it becomes distracted. So this is what happens to chlorine in your water. Say we have something like this. That's an ammonia molecule. It's sweat, urine. That's a main contributor to bad water. It enters your water, right? You add chlorine to get rid of it, to break it down. Your chlorine, which should be killing algae and killing other things, is now combining with this ammonia that's entered the water. And it forms this thing called monochloramine, meaning mono meaning one. So there's one chlorine attaching to the middle of that molecule. As we add more chlorine, it becomes dichloramine, di meaning two. And finally, we create this thing called trichloramine when those three chlorine molecules attach. And then that trichloramine actually becomes airborne. And that's the thing when you're in a commercial pool environment. I don't want to knock hotel pools, but bad hotel pools have this burning chlorine odor, and that is trichloramine that has now gone into the air. We want that process to happen. We want this ammonia to be broken down. Ideally, we break that down with an oxidizer, or we prevent it from happening, or we go after it in other ways. But chlorine goes after it pretty aggressively, forms this trichloramine, goes into the air. And in a hotel pool that has very poor air exchange, that stays in the air, lingers, and then because it's heavier than the air around it, actually reabsorbs into the water. And now you have this overabundance of trichloramine, of combined chlorine in the water. That's why air exchange in an indoor pool setting is so critical. But this is what happens to most of the chlorine that you add to the water. It's not sitting there as residual waiting for something nasty to enter the water. It's combining, typically with ammonia, typically with other elements, and it's being combined and not nearly as effective. Very ineffective killer, combined chlorine. So what we want chlorine to really go after are these elements. We want it to go after algae, bacteria, viruses. That's what we want chlorine. That's the reason that it's in the water. Those other things in the water we can deal with in other ways, because the stuff that chlorine does go after is stuff like sweat, urine, ties up. Lotions and sunscreens are a big one. Metals should be on this list as well. Metals are a big one that chlorine ties up with. Also, what is that? Chlorine goes after everything that goes in the water. Even if you don't know what it is, chlorine goes after that. And we don't want to use up our valuable chlorine to go after those things. We want it to go after the bad stuff in our water. That's why I like to tell pool people, if you just like friends of mine who are buying a pool, how do you operate it? You give your chlorine a friend. It's called the buddy system. Give your chlorine a friend. Don't let chlorine go out into the world on its own, because it's very distractible and it gets confused and it goes after every other things. So we give chlorine a friend because chlorine goes after everything in the water, not just the bad, but the nuisances as well. So we try to get rid of those. So what do we call the buddy system? What friends can we give chlorine? The obvious ones we can give them are an algicide. People have been using algicides in water forever. Algicides are EPA registered killers of bacteria, and they do an amazing job, and they're very effective. We can also add clarifiers to the water. If you add a clarifier to the water, it combines things in the water that you can then filter out. So is it a slightly more natural way to get rid of things in your water than an algicide? Sure. It allows filtration to remove it instead of killing and then removing like an algicide does. You can add an enzyme to the water. Enzymes break down oils and long chain molecules. It's the idea of turning apples into applesauce. Throw an apple out into your backyard this summer and see how long it takes to disappear. Now take that same apple, turn it into applesauce and pour it in your backyard, and you'll see that it breaks down so much quicker. That's what enzymes are there for. Enzymes should be in every body of water, hot tubs especially. They break down many things that take chlorine forever to break down. So enzymes are amazing. Borates. I will say this forever. Borates should be in every body of water as well. They have so many benefits, including preventing algae. They're a wonderful algistat. And then keeping your pH balanced is the key. Now, A typical chemical line will have 100 different SKUs, and no pool needs all of them. You simply need to make sure your water is balanced, make sure it has chlorine, and then make sure you're giving it a friend. If you want to give it two buddies, great, but giving it at least one is ideal. I'm a big fan myself of enzymes and borates because borates do an amazing job, chlorine does an amazing job, but enzyme fixes that little niche that the other two products don't do. The buddy system is key. The buddy system doesn't have to be chemistry as well. The buddy system could be a UV as an add-on that helps kill bacteria and things in a different way. Could be minerals. I love a mineral system. They typically add things like activated carbon and also metals. I'm not a huge fan of continually feeding metals into a pool, either through an algicide or through minerals, but the added benefits of adding minerals to the water do kind of outweigh the negatives of adding a mineral system. So it's great, and it definitely helps your chlorine do the job it should do. Another one is ozone. Scott, I just told you about this at Water Shapes University, just wrote a great article from a friend of yours. And I want you to read that one. I know you're not a big reader, but take the time and read it. My son read it. He loved it. He asked me why I don't have an ozonator, but a great little article, not little. It's War and Peace on ozone, but it's really, really good. And I highly recommend it. But again,
I'll read it after this. One
good.
sentence at a time. I just take one sentence, I read it, and then I think about it, and then I take another sentence.
Have AI just give you a summary of it. That's what I find is how the world is working. Ozone is great, but also anything that gives chlorine a friend, because these things do the job that chlorine does without forming this combined chlorine that then you have to overcome. Combined chlorine is essentially chlorine giving itself its own hurdle to jump over constantly. So we do have side effects that come from these systems that are small, negligible as compared to what chlorine may do. But these guys on your screen can't do it alone. The friends of chlorine can't do it alone. You need chlorine there, and you just need these as a buddy. So this is the ideal. This is water balance. You want water balance as a straight life, as a straight line. And the reason I threw life in there, because I was thinking about my next sentence, it's what you want in life. You want today as a person of a certain age, you want today to be the same as tomorrow. You don't want brand new headaches in your life over and over. You just want a happy, consistent amount of life, and you want a happy, consistent amount of water. You want water to be balanced and equal. And how do we do that? We automate. And I'm not talking about these fancy automated equipment, but those are amazing. I'm talking about automating your water chemistry. And how do we do that? We automate our sanitizer by adding a chlorine feeder, by adding a salt chlorine generator to produce chlorine. We don't want to rely on over-the-side additions of chlorine, especially if you're forgetful, especially if you're not doing it on a routine basis. If we can automate our sanitizer where we know exactly the amount of chlorine that is always going into the water, it's key. Now, obviously, when you talk about automating chlorine with a feeder or salt chlorine generator, you're talking about running your filter circulation system on a regular basis. And in my mind, a regular basis is 24/7 from the time you open to the time you close. But a routine amount of circulation is key, whether it's 8 hours or 12, 24 is ideal, but that consistency is key. How do we automate pH? We have the right amount of buffering in place so that pH is automated. It's always locked into the same spot or as close as possible. So we add proper buffering. We make sure our alkalinity is in place. Ideally, we have borates in the water to keep that pH in place. We add this word that we've been using for a while, this fake word called cleanation. We automate that. Again, you run your filter 24/7. We automate our cleaning through a robot that's in your water all the time. If you're relying on your son or daughter to go out there and clean your pool, well, guess what? They already left the house, and 20 years ago they would have been at the mall, but who knows where they're at now, but they're not cleaning your pool. Run your pool 24/7. If you got a robot, that's great. Cleanation is key. You've got to try to automate that as good as possible. Unfortunately, water balance is not a straight line. Water balance moves up and down because things enter your water that are out of your control. So now, instead of automating, we got to do this other thing. We automate, then mitigate. And mitigate means we got to try to do the best we can to deal with these problems. And how do we mitigate contaminants? We add hygiene to our normal pool operations. Make sure the people that enter your pool are clean, and make sure that the things that they do, can they shampoo get or rinse the shampoo or conditioner out of their hair? Can they keep their feet clean? Can they make sure they don't pee in the pool? Those are all things you can try to control in terms of household swimming. We can also add covers. Automatic covers are amazing. Manual covers prevent things from entering your water. If you're running your automatic cover overnight, 8 hours, you're getting a third less contaminants in your water than someone that doesn't have a cover. And during pollen season, you know how big that is. And that pollen season lasts typically in my territory from April until October, it feels like. It never ends. It's one plague after another. If you read the first couple chapters of the Bible, they're really the plagues are describing the pool environment back then. They are really dramatic. Once you're through with one, comes another one. I would not be surprised if frogs start falling into my pool. They're just constant, and the cover does an amazing job of preventing that. How do we mitigate imbalance? Imbalance happens because people enter the water, rain enters the water. We mitigate imbalance by constantly testing and adjusting the water. And constantly means on a regular basis. So if you get a normal week without too many swimmers and too much weather, we can test a couple times a week, and then we adjust the pool chemistry. After a rain event, you want to test to make sure to see where we're at as well. We don't want to be testing 2 or 3 times a week. We've got a lot of engineers out there that are testing multiple times a day and making adjustments, and it's too much. We simply need to test on a routine basis and adjust based on those test results. If you don't trust your test results, then you shouldn't be adjusting to those test results either. So make sure now is the time. Make sure your test strips are up to date. Make sure your testing equipment is verified so that you get great test results. The other things we can try to mitigate are bad openings. The only way to do that is with a good closing. And we are way past the horses out of the gate at this point. How do we mitigate a bad opening? We open as early as possible. That means we open hopefully in cold weather. And right now we're in 60-degree temperatures pretty consistently here in Michigan. Folks farther south, if you haven't opened your pool yet, it's getting to that point where opening that pool and the water has turned green underneath because the closing wasn't as good as it could have been. Now we're talking about hundreds of dollars and weeks of the season that we might be fighting that. Well, let's talk about one slide on opening and closing. A pool opening is like a car accident. There's nothing you can do once it's happened. You simply have to deal with those results. And maybe it's a fender bender, or maybe it's totaled. There's nothing you can do with it. You're going to walk into it and you're just going to have to deal with it. It's life. You just can't sit there and cry about it. You deal with the opening. What's critical is a proper closing. I was talking to you, Scott, about this beforehand. If you are a pool owner and you want to pay and you're cheap and you're only going to pay for either a closing or an opening from your local pool guy, boy, the closing is the key. And it's a lot like we were talking about. It's a lot like if you own an RV or a trailer, that so many things can happen over the winter because the closing wasn't done correctly, that really you're dealing with at the opening period. But the closing is critical. So it has everything to do with making sure the right chemistry is in the water, making sure the pool is sealed correctly. And then who's your buddy at closing time? You can't let chlorine do all the work. So a pool closing, even with a mesh cover, can open in the spring clear if you add the right buddies to the system. Chlorine lasts 10 days, 14 days under a cover when you close it. So what else is doing the job to keep your pool clear during the winter? If you have a lot of metals in your water, are you adding metal sequestering products over the winter to make sure that those don't stain? What are we doing with calcium as cold temperatures happen? Calcium falls out of water. We aren't even mentioning calcium. Forget I said it. That's the next presentation. That's part 2. That's calcium strikes back next time. But who's your buddy in the water that stops that? For me, it's borates in the water. Borates prevent algae, and that means when I open my pool, it is clear under a mesh cover. And that's the key. Closing is the key. We've talked about chlorine, pH, alkalinity, borates. We've talked about the buffering system. We've talked about giving chlorine a friend. There's our buddy right there, whatever you choose. But there are still other problems. And what are those other problems? We have the sun. And unless you're living in some Alaskan province, I don't think there's a province in Alaska, in some part of the upper Antarctic, you're going to be dealing with the sun quite a bit. So what happens to chlorine in the sun? The UV destroys chlorine. It breaks the bond to free chlorine, and chlorine goes away. And how fast does it go away? It goes away pretty fast. And most folks who've seen this presentation know 90% of chlorine that is unstabilized goes away in 2 hours. And 50% of the chlorine you add to your water is gone in 17 minutes due to UV. That's a dramatic amount of chlorine that's lost due to sun. So early pools that were using unstabilized chlorine, that were using cal hypo and liquid chlorine only, those folks had to consistently add more chlorine to the water to keep up with it. So then some products were developed. Let's talk about those right now. Let's talk about stabilized. So these are our unstabilized chlorines again that we mentioned. Sodium hypochlorite is an unstabilized chlorine. They do not have stabilizer or cyanuric acid in them. Calcium hypochlorite is an unstabilized chlorine. This goes under a lot of brand names, Cal Hypo does, but you can look on the label in the fine print and find the percentage of Cal Hypo on the packaging. Unstabilized chlorine. Also, salt chlorine generators create an unstabilized form of chlorine. In fact, all three of these products add chlorine to the water and it forms the same hypochlorous acid. This is a great way, the only ways to add unstabilized chlorine to your water. And these are tremendous products for treating or for consistently adding chlorine that's unstabilized to your water. Let's talk about cyanuric acid, which is CYA, stabilizer, UV, conditioner. It goes under a lot of names. They first synthesized, they first made it in 1829, and it became a trichlor and dichlor product in 1959. Most folks didn't see it hit the market until the early 60s to mid 60s. Cyanuric acid. If you add 25 parts per million of cyanuric acid, you get 3 to 5 times longer life versus unstabilized. So you're talking about 6 to 10 hours of chlorine life in your water with cyanuric acid. Cyanuric acid above 50 parts per million has no additional benefits. It does nothing to help your chlorine system. It stabilizes all forms of free chlorine. So if you add the right amount of cyanuric acid to the water, then you could add unstabilized chlorine to it and it becomes stabilized chlorine. Cyanuric acid has a relatively, or quite frankly, a very low pH of 4.5. And about 2 pounds of it is all you need to get 25 parts per million in about a 10,000 gallon pool. We have seen very high amounts, over 100 part per million of cyanuric acid, start to affect plaster pools, gunite pools. We definitely want to worry about our cyanuric acid buildup in those specific structures. Here's your stabilized chlorine that has cyanuric acid built into it. So when we're going to talk about these products, we're going to talk about trichlor and dichlor. Both of those products start with the cyanuric acid molecule and then create the chlorine around it. You cannot have trichlor, you cannot have dichlor without cyanuric acid. It is essential. It is actually the heart of the system. So there is no trichlor that has less cyanuric acid in it. So trichlor comes in tab form. This is the 3-inch tabs that is ubiquitous in the pool industry. This is what everyone uses. This product is a staple in the pool industry. It also comes in granular forms that we use occasionally to treat certain different algaes. Trichlor is 52% cyanuric acid. You need to be aware of how much cyanuric acid you're putting in your pool because it's slowing down sanitation, but the right amount of trichlor into the water and the right amount of cyanuric acid in the water automates your chlorine, and that's what we want. Trichlor is probably the lowest pH product most consumers will add to your water. It has a pH between 2.8 and 3.5. If we remember Henry's law, where your pH is always slightly creeping up, well, if you're adding a product at a 1 to 3 part per million with a slightly lower pH, we do offset that a little bit. So it's a great product in terms of slightly keeping your pH from rising. It's very slow dissolving. The key to a chlorine tab is we want it to dissolve in as slow as possible. We put it into a feeder that dissolves it at a very slow rate. And the product itself is compressed at a very high pressure rate so that it becomes so hard that it dissolves very slowly. Folks are very familiar with buying cheap product that dissolves very quickly or crumbles, or even it has the capability of, if you're able to snap a chlorine tab with your hand, it is a poor chlorine tab. It should be rock hard and dissolve very slowly. That's what we want. Dichlor is typically almost exclusively a granular product. It's 54% cyanuric acid and has a nearly neutral pH. It's very fast dissolving. There are times when it is pressed into a tablet or a briquette, but it does dissolve so fast that it's almost unnecessary. But those are your two stabilized chlorine products. Those are the two products. When we add it to the water, it's adds stabilizer to it. Sometimes these products, especially dichlor, can be blended with other things, buffers and clarifiers that will lower the percentage of chlorine in that particular product. So these fall under a lot of different brand names, under our names and under other manufacturers' names. So if they have lower percentages of chlorine in them, they're typically blended with other things for different various reasons. Your stabilized chlorines, your dichlor and your tabs, essentially block out some of the UV, if you want to think about it that way, and they have a longer life in the water. The way I typically talk about stabilized chlorine and cyanuric acid is that if you're adding chlorine to the water that's unstabilized, you're adding it all at one time. It all goes into the pool. With stabilized chlorine and cyanuric acid, all that chlorine goes into a basket. And now I'm handing it out. I'm distributing it slowly, one at a time, as needed. And that's what's happening. If we add too much cyanuric acid, the pace at which you're handing out chlorine slows to a pace that doesn't keep up with the contaminant level. And that's really the concern. We're going to talk about it, I think we are, on this next slide. I want you to think about cyanuric acid in terms of time. So this is from a classic CPO course, Certified Pool Operator course. We're going to talk about fecal incident response recommendation. And if you've ever taken a CPO course, trust me, the word fecal will come up 106 times. So we're talking about a fecal incident in 2016. And I want you to think about this as baby food and not Baby Ruth. And this mention, this reference for the younger audience, I'm starting to lose them because I don't think they all know what we're talking about here with the Baby Ruth, and we need to train them. I think Caddyshack might need to be part of a step one, a prequel to this, so they explain it a little more.
Anyone who hasn't seen Caddyshack, well, they need to go out right now and see that.
100%. So this is an event in 2016. This is an actual event, and this is how we treat this. Mr. Peanut has entered the water. If you don't know Mr. Peanut as well, you haven't seen my other presentations, according to the CDC, the average human being has a half peanut size amount of feces on them at all time. 1/2. Do not be above average. So say we have no cyanuric acid in the water. We get this baby food event. We add 20 parts per million of chlorine, and it takes almost 13 hours before we can open that pool up again. And we say, hey, that chlorine killed everything in the water. And we know it's safe. We know it's done its work. 20 parts per million, almost 13 hours. Pool is opened. Everyone is happy. But let's say there's even a small amount of cyanuric acid in the water. And in this case, it's 15 parts per million. 15 parts per million dramatically slows down this chlorination process. Now we go from 12.75 hours to 28 hours. It still does exactly the same job. We're putting the same amount of chlorine. It still killed the exact same amount of contaminants. It just took 28 hours to do it because we need to overcome that giant slug of baby food. We need to do it, and the only way to do it is with time. The other thing we can change in that equation is increase the amount of chlorine. If we increase the amount of chlorine, then we can cut that time down. But as we increase the amount of chlorine, we might increase the amount of other contaminants to the water. For example, we might be increasing cyanuric acid, or we might simply just make the water much more aggressive because chlorine is a very aggressive product. Again, that is for presentation number 2. So how do we get rid or deal with too much cyanuric acid? The prevention is key. And this is a big part of it right here when we talk about prevention. Studies have shown that only 10% of chlorine is utilized in sanitation, while 90% of chlorine is used for oxidation. And what does that mean? Chlorine is a wonderful oxidizer. Chlorine goes into the water and oxidizes contaminants. Putrescible elements is the way to describe oxidation. It takes something that is putrid or fouled, it changes the chemistry and turns it into something that is no longer putrid. So chlorine, which should be going after the bad things in your water, and ideally should just be sitting there as a residual waiting for those bad things, 90% of the chlorine you add to the water doesn't do either of that. It simply goes in and starts oxidizing other things in your water. And most of those other things aren't bad or can't be dealt with or can be dealt with other products. Those things that it's oxidizing, enzymes would do a better job of taking care of, or simply a non-chlorine oxidizer would do a better job of. So if you're adding a whole bunch of chlorine to make sure you have a chlorine residual, well, guess what? It's probably going towards other things, other uses other than the thing you want it to be used for. So we're adding extra chlorine. And if we're doing it through granular chlorine like dichlorine and trichlor, we're increasing our cyanuric acid, which slows down the process. We want you to have chlorine in that water. We want you to have stabilized chlorine in the water, but there's no need to overdo it by using chlorine for the wrong things. So if you aren't preventing, oxidizing, or filtering contaminants, your chlorine will combine with them. You can simply deal with this through extra prevention, extra oxidizing that isn't a chlorine-based oxidizer, and then increasing your filtration. And I would say if you're filtering less than 24 hours, that's the easiest thing to do. If you can filter 24 hours instead of 12, you're doing a much better job keeping your pool clear than any chemistry can do. Filtration, filtration, filtration is the key. Overstabilization is caused by too much cyanuric acid. It's amazing that I'm writing this and reading this, but I don't know that when I talk to people throughout the season, I talk to a lot of homeowners, this concept is very, very hard for them to understand. My pool has too much cyanuric acid in it. It's too overstabilized. What do I do? Well, you have to remove cyanuric acid, and the only way to remove it is to remove water that has cyanuric acid. Okay? Then they will say, I can't afford to take out water and add more water. It is very tricky because this is much like the opening the pool car accident. There is nothing you can do to prevent this at this point. You simply have to deal with it. You have to deal with water that is overstabilized by removing the cyanuric acid from the water. So again, let's look at this slide one more time. If we go through a normal pool season and we say, man, we've added a lot of cyanuric acid to the water, it's increased and increased. Well, if you're not maintaining your pH in the right area, you might be adding 3 times as much chlorine, and you might be adding 3 times as much stabilizer along with that chlorine. So simply maintaining a correct pH helps mitigate how much cyanuric acid goes into the water. So this is a big one. If we want the right amount of free chlorine, hypochlorous acid in the water, just maintain your pH in the right zone and you can dramatically decrease the amount of stabilized chlorine you're adding to treat your water. Remember, we need to deal with these issues with other products other than chlorine. Boy, chlorine does a great job of a lot of things, but what it doesn't do a great job is dealing with things that create combined chlorine or take up much of the chlorine's needs instead of going after bacteria. Remember the buddy system. Remember to give chlorine a friend. You don't have to give them all of the friends, but give them a friend so that it allows chlorine to do the job that it should. You've got chlorine, you've got pH, you've got your buffers in alkalinity and borate. When we come back to this presentation, I think we're scheduled for after the pool season, sometime around October. We'll talk about how these elements affect LSI. We'll talk about these elements and how adjusting these elements greatly affect how LSI works to preserve your pool equipment and keep your pool equipment clear. We also definitely want to talk about the inverse of that is maintaining your LSI needs to be at the right levels so that it doesn't act detrimentally to maintaining your sanitation of water. And a big part of this, and I'm going to leave you with, it's the war on calcium. I'll talk about that in October. What does it mean and how does it affect sanitation and LSI? And folks, I think that's it for me. This might be the first time I've actually gotten through my entire presentation. I tried harder. So I hope you enjoyed it, guys, and feel free to throw out as many questions. I'll try to answer as many of them as I can in the next few days.
Well, yeah, as a veteran of your presentations, I was hoping you'd get those all in. You did. Really impressive, John. I enjoyed the metaphors. The people in the chat enjoyed the metaphors that you used. There were way more questions than we have time for today, but we can get to them individually. But we do have time for a couple. And we'll start with Jonathan Kunkelman, who I think asked a very good question. He says, so treating a bacterial issue, would it be advantageous to lower your pH for a while you're attacking the bacterial issue and then raising it back up to 7.2 before resuming swimming?
That's a great question. And it's exactly the mindset I think of when I'm treating a pool. Lowering the pH below neutral always runs the risk, and we'll talk about that in October. It runs the risk of having aggressive water that we're running through our system. But it also is a guarantee that you're getting the most out of your chlorine. So absolutely lowering that pH level, especially if you're above neutral. The first thing I do if I have a green pool, I make the assumption, I'll do the testing, but I make the assumption that the pH is high. So I'll lower it so that when the chlorine is added to the water, typically an unstabilized chlorine, I know my chlorine will be working at its absolute peak because the pH is lower. So absolutely take advantage of that low pH, low chlorine as a treatment. But we definitely don't want to do that on a long-term basis. Just as a side note to that, a former CEO of Haviland, Bernie Haviland, always runs his pH well below 7, runs his chlorine well above 10, resurfaces his pool every 3 to 4 years. His water is crystal clear, but he's doing it at the detriment of his pool surface. But his water is spectacular for that very reason. He's got chlorine churning at the highest rate that it possibly can. But if you do that for too long of a period, we're definitely going to talk about some damage. So think about that. But definitely, the pH is tremendous to think about.
Sounds like a very clean pool.
Oh,
A question from Mark Lucas. Do borates reduce algae growth by sequestering CO2 that algae would need to grow?
So it used to be described as it oxygenating the water. Borates stop algae growth. Some articles I've read, they talk about preventing the CO2 from allowing the algae to bloom or to grow. That's the way I was always taught. That was the way it was described to me. I have some literature that talks about that for sure. There are other newer readings that I've seen that talk about it in a couple different other ways in terms of on a cellular basis, but describing it as preventing the CO2 from getting to the algae, I think, is the way I was always taught, and it's the easiest way for kind of me to understand it as well.
Okay. We have 1 minute left. We have time for one more question. This is from Christy Sweeney, who asks, I'm from California. We don't open or close our pools. Do you have any suggestions for our winter season treatment?
So if you're not opening and closing your pool, then you typically will, that straight line that we talked about earlier on that diagram, that's a little easier for you guys because you don't have this hibernation period where things can go bad under the cover. So definitely, if we're talking about colder temperatures, and we usually think about colder temperatures as anything below 60, it really starts to slow down algae growth. So if you're in an environment, depending where you are in California, that you're consistently at 60 degrees or below for a period of time, maintaining circulation, maintaining filtration, you can dramatically reduce the amount of chlorine you put in your water in cold temperatures. That's why I always tell folks in colder environments, as long as it's not freezing, get the circulation system running. You barely have to add chemistry to it because algae won't start to bloom. Having a borate in the water is going to prevent that algae. And so we don't need to add anything else. But there's unfortunately we run into this when pools are dormant, when they aren't being used, people stop cleaning them, they stop adding chemistry, and
Hmm.
that can be bad. The worst is they stop running the system as much. They see the electrical bill for these months where they're not in the pool. I would definitely say if you're not going to be in the pool on a regular basis over a given period of time, month, week, turn off the heater, keep the filtration system running, but don't stop circulating the water for any reason. That's really a key.
We'll take that to the bank. I think that'll do it for today. John, I want to thank you for an entertaining and informative hour. As always, I learned a lot. And I want to remind everyone to look forward to the sequel to this in the late fall. Um, and I just want to thank everyone for coming to the webinar. I know everyone's got a lot left to do today, so we'll all get back to the pool business. See you next time.
Yeah, thanks, Scott. Thanks, everybody.